Welcome to the session on parametric equations, review exercises. The objectives for this session are to review previous topics through exercises, namely, rearrange equations to change the subject of an equation, write algebraic expressions in alternative forms, state the range of a given function, write down the equation of a circle given its centre and radius, and find the number of intersection points of a circle and a straight line by finding the discriminant of the resulting quadratic equation. We will now solve the review exercises shown on your screen. Pause the video and have a go. Press play when you're ready to view the solutions. In exercise 1 part A, we are asked to rearrange x equals 3t minus ct in order to make t the subject. So let's solve this. So we have x equals 3t minus ct. If we factorize this, we obtain x equals t times 3 minus c. In order to make t the subject, we're going to place t on the left-hand side, so we simply interchange the left and right-hand sides as shown. And then dividing through by 3 minus c gives us t equals x over 3 minus c. Now let's take a look at part B. We are required to rearrange y equals 25t squared in order to make t the subject. So let's solve this. Again, we're going to interchange the left and right hand sides and then divide through by 25 and square root to give t equals plus or minus root y over 5. And now for part C, we are required to rearrange y equals 8 ln of t plus 2 in order to make t the subject. So let's solve this. Eight ln of t plus 2 equals y implies that 8 ln of t equals y minus 2. We've simply subtracted 2 from both sides. Dividing through by 8 gives us this expression. We now raise both sides to the power e as shown. This now allows us to make e to the power ln of t equivalent to or equal to t. And so we have t equals e to the power y minus 2 all over 8. Now let's have a go at part D. We are required to rearrange x equals 3 plus 5 e to the minus 4t in order to make t the subject. So let's solve this. Here's our equation. We're going to rearrange this so that we have the t's all on the left-hand side, as shown. And in the latter step, we've subtracted 3 from both sides in order to further isolate the t. Next, we divide through by 5, as shown, and then take the natural log of both sides, as shown. So we have that the left-hand side is equal to minus 4t ln of e, and the right-hand side stays as it is, namely ln of x minus 3 all over 5. And of course, ln of e is simply 1. So therefore, minus 4t ln of e is equal to minus 4t. And therefore, dividing through by -4 gives us that t equals -1/4 times ln of x minus 3 all over 5. Now let's have a go at review exercise 2 part A. We are required to write 7 plus 5 cos squared x in terms of powers of sine x. So let's solve this. If we replace cos squared x by 1 minus sine squared x, and then multiply out the brackets as shown, and finally tidy up, we have that 7 plus 5 cos squared x equals 12 minus 5 sine squared x. Now for part B. We are required to write sine 2x in terms of powers of sine x. So let's solve this. Using the double angle formula for sine, we have that sine 2x equals 2 sine x cos x. And then replacing cos x by square root of 1 minus sine squared x gives us 2 sine x cos x equals 2 sine x times root 1 minus sine squared x. And now for part C. We are required to write 2 sine x plus cos 2x in terms of powers of sine x. So let's solve this. If we replace cos 2x by cos squared x minus sine squared x, using the double angle formula for cos, we have this expression here, as shown. And then replacing cos squared x by 1 minus sine squared x gives us this expression. Next we tidy up and tidy up some more to give this expression. Now let's have a go at 3 part A. We are required to state the range of the function y equals ln of x plus 1 plus 3 for x greater than 0. So let's solve this. We're going to try sketching this curve. Here's a graph of y equals ln of x. Y equals ln of x plus 1 is simply the curve shifted to the left as shown. And y equals ln of x plus 1 plus 3 is the curve shifted upwards by 3 as shown. And therefore, we have that y is greater than 3. And now for part B. We are required to state the range of the function y equals 3 cos x for x between minus pi by 2 and pi by 2. So let's solve this. We're going to begin by sketching y equals 3 cos x. Here's the graph y equals cos x. Therefore, y equals 3 cos x is simply a stretch in the y direction, as shown. And therefore, y is in the range y greater than 0 and less than 3. Now let's have a go at part C. We are required to state the range of the function y equals x squared minus 6x plus 10 for x greater than or equal to 1 and less than or equal to 4. So let's solve this. If we complete the square, then y equals x minus 3 all squared plus 1. This now makes it much easier for us to sketch the curve. The value x equals 4 is mapped to 2, and the value x equals 3 is mapped to 1 as shown. So the range is now y greater than or equal to 1 and less than or equal to 2. Now let's have a go at part D. We are required to state the range of the function y equals 1 over 3x minus 4, where x is greater than 2. So let's solve this. Let's sketch this curve. Here's y equals 1 over x. Y equals 1 over 3x will look something like the curve you can see now. And y equals 1 over 3x minus 4 is a shift as shown. The value x equals 2, which is not amongst the values of x, is mapped to y equals 2. And therefore, y is greater than 2. We're now going to look at some theory before moving on to the next exercise. Suppose we have a line of length r and we rotate it about the origin. The outer edge of the line will form a circle when it is rotated. Let's take a look at an example. So let's consider one of these lines. Suppose it meets the circle at the point xy. If you consider Pythagoras' theorem, we have that x squared, which is the x-coordinate, plus y squared, which is the y-coordinate, equals r squared, which is the radius of the circle. And this equation, x squared plus y squared equals r squared, is the equation of a circle. The equation of a circle can also be written in the form x minus a all squared plus y minus b all squared equals r squared, where AB is the centre of the circle and r is the radius. Consider the example on your screen. Pause the video and have a go. Press play when you're ready to view the solution. The example asks you to write down the equation of the circle with centre 3, 2 and radius 5. Apply the equation of the circle formula to this example. Since x minus a all squared plus y minus b all squared equals r squared has centre AB and radius r, we replace a by 3 and b by 2 and r by 5 to give x minus 3 all squared plus y minus 2 all squared equals 5 squared, which gives x minus 3 all squared plus y minus 2 all squared equals 25. We're now going to look at some theory before moving on to the next exercise. A straight line can intersect the circle 0 times, as shown in the illustration, or once, or twice, as shown. We can find the number of times a straight line crosses a circle in the following steps. Substitute the equation of the line in the equation of a circle to obtain a quadratic. Then find the discriminant b squared minus 4ac in the quadratic, ax squared plus bx plus c equals 0. If b squared minus 4ac is less than 0, then we have 0 real roots. In other words, there are 0 points of intersection between the line and the circle. If b squared minus 4ac equals 0, then we have 1 real root. In other words, 1 point of intersection. And if b squared minus 4ac is greater than 0, then we have two real roots, in other words, 2 points of intersection. Let's now have a look at an example. Pause the video and have a go. Press play when you're ready to view the solution. The example states, show that the line y equals x plus 2 meets the circle x minus 1 all squared plus y minus 4 all squared equals 25 2 times, and find the coordinates. So let's solve this. If we substitute the equation of the line in the equation of the circle, as shown, then we obtain x minus 1 all squared plus x minus 2 all squared equals 25. Expanding, x minus 1 all squared gives us x squared minus 2x plus 1. And expanding x minus 2 all squared gives x squared minus 4x plus 4. And of course 25 remains as it is. Then tidying up gives us 2x squared minus 6x minus 20 equals 0. As shown. Finally, dividing by 2 gives x squared minus 3x minus 10 equals 0. In order to find the number of roots of this equation, consider the discriminant b squared minus 4ac. This equals minus 3 squared, which is 9, minus 4ac, which is 4 times 1 times minus 10. This equals 49. Now, since the discriminant is greater than 0, there are two solutions, and therefore the line meets the circle twice, as shown. We will now find the 2 points of intersection. Applying the quadratic formula to 1x squared minus 3x minus 10 equals 0 gives x equals minus minus 3, which is plus 3, plus minus the square root of minus 3 squared, which is b squared, minus 4ac, which is minus 4 times 1 times minus 10, all over 2a, which is 2 times 1. This simplifies to x equals 3 plus or minus root of 49 all over 2. And of course, square root of 49 is 7. So x equals plus 5 or minus 2. Therefore, the 2 points of intersection occur at x equals 5 or x equals minus 2. When x equals 5, y is equal to x plus 2, which equals 7. By substituting x equals 5 in the equation of the line. Similarly, we can find the y value when x equals minus 2. Again, substituting in y equals x plus 2 gives us that y equals 0. Therefore, the points of intersection are 5, 7 and minus 2, 0. As shown. This brings us to the end of this session. If you have understood its contents, you should be able to rearrange equations to change the subject of an equation, write algebraic expressions in alternative forms, state the range of a given function, write down the equation of a circle given its centre and radius, and find the number of intersection points of a circle and a straight line by finding the discriminant of the resulting quadratic equation. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.